much. So in this last of the 3 lectures, I wanted to describe another example where a careful understanding and analysis of molecular emissions in this case can tell us something about the interstellar gas that is of general interest in astrophysics. And this concerns interstellar shock waves, which are actually quite a widespread phenomenon in the interstellar medium. Maybe I could again, by sort of show of hands, find out how many people are molecular physicists primarily, and how many are astrophysicists. Okay, so that's good. That means I could try and pitch it to everyone. So, which is what I had intended. So let me start by just giving a bit of an introduction to this phenomenon of shock waves in the interstellar gas. And the reason shock waves are important is that there are many phenomena in astrophysics that give rise to supersonic flows. So the most dramatic example is the supernova explosions that happen at the end of the life of any star that's more massive than about 8 times the mass of our sun. And these send blast waves out that can live for tens of thousands of years and just sort of expand into the surrounding interstellar gas. And the initial velocity of the material that's ejected by the supernova can be 10% of the speed of light. So it's a huge amount of energy. Another important but less dramatic example is associated with the birth rather than the death of stars. And when stars form, they do so through what we call an accretion disk. So the material falls in, it falls onto a disk that then has the material spiral into the forming star. And while the main story, of course, is the infall of material, this is always accompanied, it seems, by an outflow of gas along the rotation axis of the disk, which we call a protostellar outflow. And the gas there can be moving at 100 kilometers per second. So both of these are very high velocities relative to the sound speed in cold interstellar gas clouds, which is typically a couple of kilometers per second, as is the Alfvén speed that I'll get to in a minute. So then there's a question, what happens if you have a supersonic flow that encounters an obstacle like a surrounding interstellar gas cloud? Well, if the flow is subsonic, then the gas basically can move out of the way, can move around the obstacle, because it's possible for information pressure gradients to propagate upstream so that the gas can sort of be told, move out of the way, there's an obstacle coming. It'll set up an appropriate pressure gradient to have the flow diverted. But if the flow is supersonic, then there's fundamentally no way for the information that an obstacle is there to propagate upstream. So the flow cannot be perturbed until it encounters the shock front, which is a place where the bulk velocity of the supersonic flow and the kinetic energy associated with that is very rapidly turned into random thermal energy, and the temperature rises, and the gas decelerates. Then on the other side of the shock front, it's subsonic and then can be diverted. So this shock front is typically a thin region where the kinetic energy of the bulk flow is rapidly converted to random thermal energy. And the temperatures achieved behind a shock front can be very high. Basically, KT is going to be of order 1/2 m times the square of the shock speed. So this case, and in particular the case where a shock front is very narrow and the gas is suddenly heated and then flows through the shock front and cools afterwards. This case is something that I considered for my thesis with Alex, actually, with Alex Dalgarno. And we investigated how the temperature would return to its equilibrium value as the gas flowed behind the shock front, how molecules which had been initially destroyed because of the high temperatures would eventually reform, and the types of emission that would emerge. And the types of shocks that I consider in my thesis are called dissociative shocks because they are fast enough, and this means a speed of a few tens of kilometers per second, fast enough to dissociate molecules. So that's the simple picture. There's a slightly more complicated picture that comes into play. This is because of the fact that often the interstellar medium is weakly ionized, and there's magnetic fields that are dynamically significant. And in that case, you could really imagine the gas that is flowing into the shock front as two interpenetrating fluids. So there's a fluid composed of the neutral particles, so mainly molecular hydrogen. And then you could think of this as being penetrated by a fluid containing charged particles, ions and electrons. And they might be much less abundant in dense molecular gas because the gas is primarily neutral, and there's only sort of small amounts of ionized species that actually result from cosmic rays ionizing the gas. But because you have this magnetic field, the ionized fluid can behave quite differently from the neutral fluid. Because the ionized fluid feels the Lorentz force associated or imparted by the magnetic field. And then the neutral fluid is often very well coupled to the ionized fluid because of collisions, but the coupling is not necessarily perfect. So that to treat this really properly, you would probably have to, or you sometimes have to, consider separately the flow of the ionized fluid and the flow of the neutral fluid. I'll just make that go away if I can. Yeah, I'm just trying to, can't see very well where my mouse is. Oh, well. Let's see. I guess I would have to get out of full screen, then close it, then go back to full screen. Okay. So we're often in the case where it's a good approximation not to worry about this fact, but in these shock waves, depending on the strength of the magnetic field, which is present, and the level of ionization, it turns out that this fact that we have two different fluids can be very important. And the reason is that the magnetic field affects the speed at which a wave motion can propagate. So, sure some of you know well that there's when you have a magnetic field, there are other modes in which waves can propagate, alphane waves. And even the normal mode of sound waves, longitudinal waves, have their velocity increased by the presence of the magnetic field. I mean, one way of thinking about this is that the medium is in effect stiffer, because if you have to compress it, not only are you compressing the gas, but you're also compressing the magnetic field. So a stiffer medium is going to give you a faster propagation speed. Now, in the neutral fluid, or if you treat the fluid as a whole, the alphane speed is comparable to the sound speed. So this isn't a big effect. But if you were just to think about the ionized fluid, then the density of ions, the mass density of ions, could be much, much less than the density of the fluid as a whole. And the alphane speed depends on this quantity shown here. It's the square of the magnetic field divided by 4 pi times the density of ions. This is all in Gaussian units, all to the 1/2 power. So what this means is if the ions carry only a small part of the mass and they were decoupled from the neutrals, then waves could propagate at much, much larger speeds, perhaps 100 times larger in this ionized fluid. Yes?
Maybe this rho, is that the total density or is that the total density of the ion?
So there are 2 rows here. So one is the total density, and one is the total density of the ions. So because the total density is much larger than the total density of ions, then the alphane speed in the ions is much larger than what it is in the neutral particles. The bottom line is then that even though our flow may be highly supersonic when we consider the fluid as a whole, if we just consider the ions, it could be quite subsonic. And so the ions could be gently decelerated, and the neutrals would be would also be gently decelerated as collisions between the ionized and neutral fluids brought them into more or less the same velocity. So I'm almost finished with this introduction. I think I could skip that. But let me turn to the final few sentences here, which is that the ions are gently decelerated, and then the neutral particles are decelerated over a length scale that depends on how far they get before they collide on average with one ion. So this depends on the cross-section for elastic scattering of ions of neutrals, and also the density of ions. But for typical interstellar parameters, this length scale can be quite long compared to the time scale on which the gas cools. And so the effect of this is that instead of having a sharp shock front where the gas is suddenly decelerated and the temperature can get very high, you have a more gradual deceleration of the gas, first the ions, then the neutrals. And the energy is released more gradually so that the gas does not get as hot as it would in this jump type shock. So those are sort of the 2 hallmarks. Bruce Drain, who I believe was a postdoc here with, I don't know if it was with Alex, but he certainly worked with Alex Dalgarno, introduced this terminology that in the case where these multi-fluid effects were important, he called them C-type shocks, with C standing for continuous because the flow variables vary continuously. And then the other type of shock, which is what I modeled with Alex and which is appropriate for very high shock velocities, he called those jump type shocks or J-type shocks. And so here's a paper that one of the key papers in the subject, which he wrote with Wayne Roberge, whom I mentioned yesterday, and Alex Dalgarno in 1983, which basically showed the structure of the C-type shocks. And what you can see in this lower panel is shows you how the velocity of the ions changes, and then lagging behind, the velocity of the neutrals change, and the gas gets heated up to a few thousand Kelvin, which actually is not enough to destroy the molecules, but just heat them up and modify their chemistry. So that's the astrophysical introduction I wanted to give to these shock waves. And now I'm going to talk about how we have been able to actually demonstrate this effect through observations of gas that has been heated up in one of these C-type shocks. So that's probably quite a lot to have covered in the introduction that isn't familiar to many people in the room. So are there any questions you'd like to ask before I go on to a topic that is probably much more familiar to the molecular physicists? Okay.
Maybe I could ask one question like this. If the speed of the ions of the shock and the rest of the gas can be the same time scale as well, if the thermalization time scale of the ions of the surrounding gas is faster in collisions, let's say, than the shock from the passes on. They not all speed up at the same rate. If thermalization is fast.
Yes, so I mean, I would call that coupling. If there's very strong coupling between the ions and the neutrals, then the velocities will be the same. So this length scale is basically inversely proportional to the degree to which the ions and neutrals are coupled. Yeah, Volker.
Could you maybe give some examples of typical J shocks or C shocks we find out
Right.
in the universe? That
Yeah.
might be very illustrating. But before we had the outflows and we had the supernova.
Right. So supernovae actually give you probably a mixture of these, because as they expand, they get slower and slower and slower. So initially, it's definitely a J-type shock. It's very fast. The ionization induced by the shock is very high. There's a very high level of ionization. So the fluids are very well coupled, and we don't have to worry about this difference. And then as they go further and further, they slow down. And once the speed gets below maybe 40 kilometers per second, then these C-type shocks come into play, particularly if the gas is propagating in gas that's mainly molecular, that can cool rapidly because of molecular emissions. So in the case of supernovae, you see both. So if you look at a young supernova remnant, you won't see molecules, you'll see ions, highly ionized species, and those are the jump type shocks, the J-type shocks. If you then look at a much older supernova remnant that has encountered, say, a molecular cloud, there you may see a slower shock that is a C-type shock.
Actually could get the age of the supernova.
Yeah, I mean, that's one way. I mean, you know, perhaps a better way is just looking at the size of the supernova remnant. Yeah. Okay. So let me go on to a more molecular topic that now connects to this. I mean, really the takeaways that are essential are that shocks are widespread in astrophysics. There are many phenomena that give supersonic motions. And there's a type of shock where the fluid flow changes quite slowly, the C-type shock, And when these propagate in molecular clouds, we can see molecular emissions from these C-type shocks. So what I'm going to talk about now is some observations of molecular hydrogen that we've made in an example of a C-type shock. And we can demonstrate that the flow velocity does change smoothly as while the gas is hot. And the way it turns out we can do this is through looking at the ortho to para ratio of molecular hydrogen. So this is just a figure from, if you've ever been to Munich airport, maybe there are other airports, as you arrive, you come down here. And actually I was arriving and giving a talk about this at Schloss Ringberg that the Max Planck Society runs in Bavaria. And, you know, it was almost like people were talking to me from discover a world of unseen potential, www.fascinatinggases.com, and then it says H2. This is from Linde, that manufactures many of these gases. Okay, so let me now take a sharp turn to molecular physics and talk about ortho and para hydrogen. So as a reminder, if we look at rotational states of hydrogen, they're very simply arranged with the usual spacing that you expect for a diatomic molecule that doesn't have any spin or orbital angular momentum. And so we see all these different transitions at infrared wavelengths. And because there's no dipole moment, and for other reasons that I get to in a minute, the change in J is always 2 rather than 1. And spectroscopists use a capital S to indicate a change where delta J is -2. And then the number inside here is the rotational quantum number J of the lower state. It's a little bit more subtle than the fact that there's no dipole moment because of the symmetry rules. So just as a reminder, with the hydrogen nuclei, you basically have 2 identical spin 1/2 particles, 2 fermions. And so the wave function must be antisymmetric with respect to interchange of the 2 nuclei. And there are 2 parts to the wave function, of course. There's a spin part and a part associated with the rotational motion. And so there are 2 cases. You could either have these 2 spin 1/2 fermions aligned, if you were, to give a total spin 1 case, where the spin part is symmetric. So that would mean the rotational part has to be antisymmetric. And that actually requires then that the rotational quantum number is odd. So that's ortho H2. And then there'd be para H2, where the total spin of these 2 nuclei is 0. And then you have to have an even part of the rotational wave function. So that means that J is even. So really, you could think of H2 as being almost 2 separate molecules, ortho H2 represented by the odd J states, and para H2 represented by the even J states. And you could then ask, well, what will be the ratio of ortho to para H2 as a function of temperature? And it will depend on temperature, because at very low temperatures, everything will fall into the ground state in thermal equilibrium. So that'll be para H2, the ortho to para ratio will be 0. But then at very high temperatures, all of these states will be very well populated. and the ratio will just be the ratio of the spin degeneracies, which is 3 to 1. So this is the author to power ratio in equilibrium as a function of temperature, going from 0 to very close to 3, say at temperatures above 200 Kelvin. And the conversion between ortho and para hydrogen is very slow. There are no radiative transitions, and in non-reactive inelastic collisions, there are no collisional transitions that can change J by an odd number. So basically all these elastic collisions or the radiation that might go on will not convert ortho and para H2. And the reason collisions are so ineffective is if you wanted to convert from ortho to para H2 or vice versa, you'd have to do two things at the same time. You'd have to change the rotation of the molecule in the collision and change the nuclear spins, which are on a completely different scale. So the implication is that ortho to para conversion is very slow. And actually, this is a well-known effect that I hadn't known about myself until I started studying this astrophysically, but it's well known in the production and storage of liquid hydrogen. So you might think it would be fairly straightforward to produce liquid hydrogen. You would just refrigerate gaseous hydrogen and cool it down to 20 Kelvin. But the problem with that is that if you do that, there's not enough time for this very slow conversion from ortho to para H2 to take place. And so basically, if you like, you freeze in the ortho para ratio at the room temperature value. So it's 3 at room temperature. At the boiling point of hydrogen at atmospheric pressure, which is 20 Kelvin, the ratio of ortho to para hydrogen should be 0.01. But if you cool it down rapidly, it's still going to be 3. There was no time for ortho para conversion. And it actually takes about a week with the hydrogen sitting in the dewar for this conversion to take place. And the problem with that is that the amount of heat released by the ortho para conversion, that amount exceeds the latent heat of vaporization of liquid hydrogen. So basically you just put it in a dewar, and if you didn't actively cool it, it would just boil away because of this ortho para conversion, regardless of how well insulated your dewar was. So actually what they do is they put a paramagnetic salt in that catalyzes ortho para conversion, I think by interacting with the nuclear spins. So this idea that if the temperature changes rapidly, you might not see the ortho to para ratio catch up to the equilibrium value it's supposed to have is also known in as an effect in astrophysics. Yes. Yeah, please.
Which extent you neglect the electronic particles of freedom? So like find interaction. Because in this treatment, you are neglecting the electrons.
Right. Right. So I'm basically, I guess, everything that I'm saying is applies to the ground electronic state. So I'm really talking about, what happens at low temperatures. And in the ground electronic state, the electrons have no spin or orbital angular momentum, so there's really no interaction. Yeah, I think that's probably the answer. Okay. So these pure rotational transitions of H2 are detectable at mid-infrared wavelengths, where Earth's atmosphere is opaque generally. So few of the rotational lines can be detected from the ground. But to get good data, you really need to go to an airborne or space platform. And we did this with the Infrared Space Observatory that operated in the 1990s. And we observed a particular source, HH54. It's a class of object astronomers call Herbig-Haro objects, where a jet from a protostar collides with surrounding gas and gives a shock front. And towards this object, we detected 5 pure rotational lines of H2. And to analyze such observations, astronomers often construct what we call a rotational diagram. So this is a log linear plot where we plot the logarithm of the number of molecules we find in a particular state, divided actually by its degeneracy. We plot that against the energy of that state. And the reason we do this is that if you're in thermal equilibrium, the Boltzmann factor e to the minus energy over kT will make sure that you get a straight line. And the slope of that line will be inversely proportional to the temperature. So it's sort of a convenient way of seeing temperatures. And we constructed such a diagram for these observations. And if we were in thermal equilibrium with the author-para ratio in thermal equilibrium, then everything would perfectly lie on the line. But what we actually see is that the even J states lie on a higher line on average than the than the odd J states. So that's telling us that para hydrogen, represented by the even states, is more abundant than it would be in thermal equilibrium. And the slope of either of these lines tells us the temperature and indicates that we have gas at 650 Kelvin. And this gas has been heated by a shock because the typical density in a molecular cloud is less than 100 Kelvin. So this shock caused by this jet has heated up the hydrogen to 650 Kelvin. But if we look at the author-to-para ratio, which would be almost exactly 3 at 650 Kelvin, it's less than 3. There's more para-hydrogen than we would expect in equilibrium. And in fact, the author-to-para ratio is only 1.2, despite the fact that this is hot gas. So what's happened, the explanation must be that initially the gas was much cooler. The temperature would have had to be less than about 90 Kelvin to give an author-para ratio less than 1.2. And then it got heated up, and the period of time for which it's hot is insufficient for ortho-para conversion to fully take place. There may have been some that got the ortho-para ratio up to 1.2, but certainly not enough to get it up to 3. So this was very interesting. I mean, it certainly indicated some kind of time dependence. You're sort of using the ortho-para ratio as a clock to measure how long the gas is hot before it cools down. And we had some detailed calculations that basically showed that we were seeing sort of what we might expect if author-to-para conversion occurred by so-called reactive collisions, where you have a collision between a hydrogen molecule and a hydrogen atom, and basically a bond is broken and you're forming a new molecule, then then you can convert from author to para H2. And this reaction and the reverse reaction, if they go long enough, will ensure that author and para H2 are in thermal equilibrium at the appropriate value of 3. This was consistent with our model for, in fact, a C-type shock. And then we got a lot more data and better data. Yes, yeah.
On the last slide, try to maybe some of the details in that calculation of using it as a prop. Does it depend sensitively on dust catalysis or the magnetic field strength to try to back out how long it's been?
No, it would really depend. What you need to know really is the density of hydrogen atoms, because that's what's doing this conversion. And you need to know the temperature, because this has an activation energy barrier that's been estimated as corresponding to about 4,000 Kelvin. So if the temperature of the gas was only 400 Kelvin, let's say, this would be really slow and there wouldn't be enough time. Or at least yeah, so that's what goes into the calculation of the time scale for the orthopara conversion. You also need to know the time scale or the time period for which the shock elevates the gas temperature, how much time is available for this orthopara conversion. And that then would get into some of the other things that you mentioned. So we then got a lot better data on this. In fact, Volker was involved with some observations we made with another satellite observatory that was very, very sensitive, the Spitzer Space Observatory. And now you can see we have 8 transitions of molecular hydrogen, all the way from S0 to S7. We've actually seen this phenomena in many, many sources. But here are 3 different positions we could observe in the same source I talked about earlier. And you can see there's this very systematic zigzag behavior indicating again that ortho and parahydrogen are out of equilibrium. What else do you notice about this zigzag behavior? And in particular, its dependence on how far you are to the left, to the right. Yeah, so it's curved, that's one thing. And that actually tells you have a mixture of temperatures, with colder gas giving you a higher slope here and warmer gas giving you a lower slope here. But what about the level of the zigzag? Maybe it's not so obvious. Say it again. The separation here? Yeah, that's true. That's to do with the rotational structure of H2. But the other aspect to this is that the level of the zigzag is less. So if we think that maybe there's a mixture of gas at different temperatures, then the lower temperature gas, which contributes most to the lower line transitions, has been less effective in seeing ortho-para conversion than the higher density gas. And that makes sense because of this activation energy barrier. You would expect to get closer to equilibrium in the higher temperature gas. So this is just a summary of what I've just said. First of all, in answer to your question, there is a curvature that indicates that multiple temperatures are present. And this might mean that we're actually seeing shocks with a range of velocities, which would not be unexpected. And then the fact we have this zigzag behavior tells us first that the ortho to para ratio is less than 3. So it's very clear the chemistry, if you like, if you want to talk about ortho para conversion being chemistry, which it sort of is, because it involves breaking bonds, then this is compelling evidence for non-equilibrium chemistry. And the departures from the equilibrium value are greater for the lower temperature conversion components. So conversion of parahydrogen to orthohydrogen is more efficient in faster, hotter shocks, as expected. Okay, So I'm finally at the new discovery that I wanted to mention. So now there's a question then, okay, in some of these shocks, particularly the faster ones, there is enough time for a para hydrogen from the cold initial state of the gas. There is time for it to be converted to ortho hydrogen. Could we actually track that happening? So the first way you might think of doing this would be, well, if we had very good spatial resolution, then we could sort of scan across the shocked region, and maybe we could see that changing. The trouble is the length scales are quite short compared to the resolution that we have in existing telescopes with spectrometers, at least the ones capable of observing H2. This might be possible with James Webb, which will be by far the largest telescope that can see all of these transitions. And I'd very much like to try and look at that. But there's another way of doing it spectroscopically. If you don't have spatial resolution, perhaps you could see this if you had sufficient spectral resolution. So if you had very high resolution spectroscopy, then you might be able to see a dependence of the ortho-para ratio on the amount by which the gas has been decelerated. So that's sort of shown in this figure here. So these are theoretical models for these shocks, a C-type shock. So the temperature rises to, in this case, about 1500 Kelvin, and remains warm for quite a long time, and then drops. And while this is happening, the flow is decelerating. So this is a shock that started at 25 kilometers per second. So the velocity flowing in was 25. This is in units of 10 kilometers per second. So that's there, the orange curve. And then it gradually decreases at the same time as the ortho to para ratio in this model is gradually increasing. So if this picture is correct, you might expect then, if the shock, unless the shock was moving perpendicular to the direction that you're viewing it, but if there's any component along your line of sight, then there would be a correlation between the velocity, which would show up as a redshift, and the ortho to para ratio. So the prediction was then that there should be small shifts between the ortho lines. So that would be the magenta one and the green one, S7 and S5 in this model, and the para lines. So you can see the sort of this shift that would be a prediction, and it would be quite unique to the C-type shock, because it would mean that the flow velocity is changing gradually as the ortho to para ratio is changing. So that's an effect that one might hope to detect with an instrument on Sophia. It's not the one that I used for the helium hydride or for the molecular ions I talked about on Tuesday. This one is called XES. So this is at mid-infrared wavelengths. And it's the one that can see these H2 lines, pure rotational lines. So we got some time for this in 2018, and we chose two para hydrogen lines, S4 and S6, and two ortho lines, S5 and S7, towards two positions in a different Herbig-Haro object, actually. Well, those were actually the most easily accessible from Sophia. Yeah. Yes. Right. I don't think there's an instrument with the right characteristics that could do the other lines. They're also actually, another key point is they're brighter. because the shorter in wavelength you go, the brighter the lines are. Actually, for quadrupole transitions, the dependence on frequency goes as nu to the fifth. So that's a big effect. So you want to look at the highest frequency transitions you can. So here's a picture of the source that we observed. It's called HH7, Herbig-Haro object number 7. And there's a jet from, it's believed, from this young star called SVS13 that is coming all the way here and then encounters a clump of dense gas and gives rise actually to a bow shock. This is part of my joke with the picture. It seemed like, you know, NATO or whatever, people were talking to me through these posters. It was, I think that's one of these magical realist movies where somebody thinks that all these signs are speaking to. I sort of had that impression a bit. So, so here are some high resolution observations from the ground of vibrational emissions from H2 and also from sulfur 2. And this shows this beautiful bow shock. And the red and the blue rectangles show where we put the slit of this spectrograph that was flying on Sophia. And if you use a small enough slit, you can get very high resolving power. So this was a resolving power of about 86,000, meaning, you know, the wavelength over the uncertainty in the wavelength is 86,000. So that would correspond to a Doppler shift of just 3.5 kilometers per second, which is sort of more or less at the level that you would need to detect this predicted shift. And now I'm going to show you what we saw. And it's exactly what this model predicted. So you can see the blue and red peaks are to the right of the magenta and green peaks. So there's a velocity offset between ortho and para H2, and the shift is 3 to 4 kilometers per second. So these are just Gaussian fits to the spectra we got, and the numbers are the central, the peak centroid frequency expressed as a Doppler shift. Here's another way of representing this, so that the velocity, Doppler velocity, is shown for the 4 lines with this clear difference.
The line widths are quite different. It's increased with
well, I'm not sure. The top spectrum is pretty noisy, as you can see, and there's a pretty large error on the centroid. So I'm not quite sure to what degree those line width differences are that significant. Well, I would take your point, actually. The green and the red are somewhat different. I'm not sure that the green and the blue are that different. Well, I don't have the figure, but we felt we got a fairly reasonable fit from the models. And I'm not sure whether the models predicted different widths. Okay, well, that's an interesting point, actually, that I don't have an answer to right now, but that prompts me to look into that again. Any other comments or questions? Yeah. Yes. Yeah. So the error. Yeah, so this is basically just, a standard way, some kind of chi-squared analysis. When you fit a Gaussian, you can determine the uncertainty in any of the fitting parameters. Right. So basically the error bars go in the expected way with the signal to noise. So I don't have a plot of that with line width, but now you make me want to make one and see actually what's statistically significant, what isn't. Yeah, these are 1 sigma error bars. So actually, you really couldn't say that S7 is shifted at a significant level from the paralines, but you can certainly say that of S5. And it's nice we have a sandwich of para, ortho, para, because people might say, well, maybe there's a mixture of hot and cold gas and they're shifted. But the fact that it goes down from 4 to 5 and then up again for S6 at a highly significant way is really showing this is something to do with ortho and para, right? It's not just to do with how energetic the upper state is. And then there's another way of presenting this where, as a function of the velocity, we sort of fit the ortho to para ratio and the temperature. And again, you can see it starts out at some very low number and then rises up towards 3 at the more blue shifted velocities that then we would say are the gas that's further behind the shot front. So basically then the conclusion is that this is another example of where careful molecular observations can show you something that is rather unique. And basically this is a good example of non-equilibrium chemistry. But perhaps most important, I think it's one of the most direct piece of evidence for these C-type shocks, because if it was a jump shock, the gas would heat up and then it would already have been decelerated and there would be very little further change in the velocity while ortho-para conversion was taking place. So then there would be no shift. So the fact we have a shift means supports the idea of these C-type shocks. So it's obviously a pretty complicated argument with many steps, but I hope I've managed to convey to you why we think this does demonstrate the existence of C-type shocks. So I've gone on a bit long, so I'll leave it there. Happy to answer questions.
Thank you.
Yeah.
Really fascinating talk. I was wondering, all the molecules also have ortho-para species like ammonia.
Right.
Do you ever use that to stop shocks?
Yes, so we don't really see emission from ammonia that we can attribute to shocks in the same way as we can with H2. So I believe in terms of shocks, this may be the best, by far the best case. But there are many other cases in interstellar chemistry where people do look at the ortho to para ratio in cold clouds, and typically it's in equilibrium, which maybe, I haven't looked at this quantitatively, but does tell you that the lifetime of cold clouds is sufficient for things to reach equilibrium. There was also a lot of interest in the ortho to para ratio in comets, where water is being vaporized from an icy object that previously was much further from the sun and was just deflected onto an elliptical orbit close to the sun. Then once it gets within roughly 2 astronomical units, twice the radius of Earth's orbit, the water starts vaporizing, and people have been measuring ortho and para water and looking at the ratio. And there were claims that it was less than 3, which maybe seem to have gone away a little bit, whether they're statistically significant. And there was also an interpretation of the fact that they were less than 3 that I think was completely nonsense and made no sense. The explanation given was that the author power ratio was less than 3 because in the ice was cold and it would have reached equilibrium appropriate to a cold temperature. And then it would be a similar effect to what we're talking about here. But that just makes no sense in an ice where the water can't rotate. So, you know, they say the same, they look at the temperature dependence of the author to power ratio for H2O, which is determined again by these symmetry considerations, and has a temperature dependence that is controlled by the rotational constant of water. But if you're a water molecule in an ice matrix, how do you even know what your rotational constant is? So I think a lot of the initial interpretation made no sense, and I think people sort of agree now about that. But then there's a remaining question, you know, it's an observational thing. Is the author to power ratio less than 3? Not sure what it would mean if it is. And apparently the evidence seems to be evaporating a little bit for anything that's different from 3. But there are actually many other instances where astronomers have been interested in author to power ratio for molecules that obviously have that feature.
Ask a very naive question. When the shift will be so shift
we can get the ratio if we have one of these plots where we're plotting n over g, we'll call it gj and g s, so spin degeneracy and rotational degeneracy, gj plus 1. And so if we get any 3 points, then we have 4, 5, and 6. Yes, it looks like this. Here's the zigzag. So you could always take those 3 and basically draw a line here. The slope of that line gives you the temperature, and then this distance gives you the author to power ratio. So basically, at each point, we could go and with 3 measurements, we can get the author to power ratio and the temperature. So that's how we did that and made that plot where we showed author power ratio as a function of Doppler shift.
Thank you, David, for hope David enjoyed this visit.
I did very much. Thank you.
Coming back home.
Yes.
Sort of.
Returning home. Yes.
Especially after such a long pandemic delay. And that's his final task ahead of him. Having lunch with the students.
Okay.
And then he will be driving south.
Yes.
So thanks everyone. And, thank you very much.
Yes, thank you. And I've really enjoyed the interactions I've had with you. And yeah, thanks for coming to all my lectures. I see many came to all of them, but a lot of stamina to listen to me 3 times in a week. So thank you.
Thank you.